functions. So the optimal hashing is you have a uniform distribution, also called a perfect hash, and all keys map to unique hash table slots. What does uniform distribution mean? It's a very simple question. So basically, normally, you guys know what is a normal distribution? Normal distribution, Gaussian distribution, bell curve distribution. Okay, there we go. So if you have a bell curve distribution, that means that this is the low, this is the high, that we have few things that are small, but then they get more of them occur as they get bigger, and they peak around the middle, and then as we go larger than the average, they start getting fewer, fewer, fewer. So you have this shape, like a bell shape. It's called a normal distribution. So that means that it's more likely that something is going to, so because it's more probability is in the center of the distribution, that means it's more likely that values are going to be around the center of the, let's say, average type value. It's less likely, because the curve goes down, that we get small values. There's a small amount of those small values, there's a small amount of those large values, and as we get to the center, it increases. Uniform distribution means that we have kind of like a square-looking distribution. That means that the probability that something is very small or very larger in the middle is the same. So the probability of anything coming from anywhere in the distribution is equally likely. That's what we like for hashing. We want the probability of any single location being the same probability. There they are. Okay. I was going to wait for you to come here, but you were not here last time. Yeah, and you also. All right. They disappear together, they arrive together. That's a good thing, okay. All right, so optimally we want this uniform distribution. All keys map to unique hash table slots, but this is so unlikely, it's not even funny. And I tried to give you an idea of how much it is, and actually I was in my office right before the class, and I had very nice stuff worked out, and I was interrupted for 15 minutes, so I didn't ever get a chance to copy. But what I wanted to show you is something we discussed last time, which was the probability of having 365 people at random having unique birthdays. And I think the probability of that, I counted the probability of that was something like 1 times 10 to the minus 153rd power. So 0.000000000, that's about 10. Well, 140 more of those. Okay, and about 3 or 4 more of those, and then you put a 1 in there somewhere. So it's not going to happen. Even if now if you go 30 people, and so I worked it out. There's a nice curve. The curve looks kind of like this. So the curve starts at 1 because the probability of 1% of a unique birthday is 100%. And the curve goes down like this, and then it just gets closer and closer to 0, like crazily closer to 0. So when you get about 30 people, so if I pick 30 people at random, the probability that they all have unique birthdays is about 50%. That's sort of the break-even point. After 30 people, the probability that they all have unique birthdays is less than 50%, and then it becomes a lot less than 50%. But once it's less than 50%, that means it's more likely that we will have at least 2 people having the same birthday than not. So if I had a class of 30 students, which I don't, and we got everybody's birthday, then we could find out that our expectation would be that more likely than not, we would have 2 people on the same birthday. Of course, we could do this experiment by including people who are not here, like your parents, or your siblings, or your wives, or your husbands, or your brothers or sisters, or even your dog if you know their birthday. But anyway, so this is very, very unlikely. So the only way we can guarantee perfect hashing is basically by doing this crazy stuff like reserving a slot in the hash table for every single possible key. But you know what can happen with that? We have a lot of waste of space. So realistically speaking, we're going to have some collisions. Typically, most keys map to unique hash table slots, but some do collide. Some are going to collide, and we have to start collisions and handle collisions. The worst possible hash table function is that everybody goes to the same location. That would be the worst hash table function of all, like the hash of anything returns some constant. Well, I don't think anybody would expect that to happen. But sometimes a realistic worst is all keys map to a subset of hash table slots. So you may have 1,000 slots, but only 100 of them get targeted. And that typically is the case maybe if the keys are some limit of keys that you expected, and then your table, first of all, how many slots should you have in the table? The answer is never 1,000, and never 1,002, never 1,004. In fact, never anything even, and never anything odd unless it's prime. So the number of slots in the hash table should be prime. So when you do a modulo, your final modulo into the hash table locations, you should get a division by a prime number. So if you need to have 1,000 slots, make it 1,001. Because then you have a prime number. I believe 1,001 is a prime number. Okay, I could be wrong, but so we have to check it out. All right, so that's the basic idea. So to avoid poor distributions, we need to be aware of the expectation of the set of keys that you are likely to see. We need to use some common sense, some intelligence in choosing the hashing function. We should simulate our hashing function with test data to see how it might perform in real applications. So simulation is a good idea to see how a function may perform. We have no way of quantitatively saying this hashing function is wonderful. We could say, see, wow, this hashing function is throwing the numbers all over the place. It's crazy. That's usually a good sign because that means it's really randomizing stuff. That's a good sign. But is it a proof? No, it's not a proof. So we might want to simulate to see whether, in fact, what we're expecting to happen is going to happen. Now, hash table of 10,000 slots. Again, 10,000 plus or minus some number to make it a prime. And let's say 8,000 employees hashed by the first letter of the last name. So that's a horrible hash function, right? All employees would hash only 26 of the 10,000 slots. Because we have only 26 different letters, so that only 26 of the slots would be targeted. So you would have a lot of collisions. How many? Well, I suppose you could say 8,000 over 26 would be the expected value of collisions on any one letter. And that's not realistic because we might not have as many people whose last name starts with the letter X. We may have a lot of people who start with the letter D, my name, but some letters are going to have few. So J would be receiving much more than, for example, some X, et cetera, et cetera, et cetera. So again, so this would be a bad idea, obviously. What's the packing density of this plan? Just see if you're paying attention from last time, if you still remember. What's the packing density of 8,000 employees into 10,000 slots? Easy question. 80%. Because packing density is based on what part of the table is being filled with records. So in this case, 8,000 out of 10,000, 80% packing density. Is that a reasonable number? The answer is yes. Packing density should be between, what's packing density for best results, roughly? Between what two numbers, what two percentages, roughly? I would say 80% would be about as big as you want your packing density to be. How about as low as what? 60, yeah, 60 to 80. 60 to 80. Again, 80 means more collisions, 60 means less collisions, 80 means less wasted space, 60 means more wasted space. Those are the trade-offs. It's not worth going less than, so somebody says, okay, 60, I'm going to go 60% because I want to have reduced collisions. And so somebody else will say, well, I want to reduce collisions even more, so I'm going to go to 40% packing density. Well, what's the argument against going to 40% packing density? No, less. 40% is going to 40% packing. So 60% is not that many collisions. 40% means even less. But why not go to 40? Well, what's a bad idea about going to 40%? You are wasting a lot of memory and you're gaining very little in terms of avoiding collisions. That's the problem, okay? So this is called the law of diminishing returns, where you basically end up giving up a lot and gaining a little. Look, you might be able to, so let's say the collisions, this is very bad collisions, and now all of a sudden it is good collisions. Good, this is pretty good, we can live with this. But now you pay twice as much from here to here, you paid this much. Now you pay that much again, and the collisions go down like this, and like this. Is that worth it? at that point. At that point, you're paying a lot, and the collisions are just, they're better, but they're not a lot better, but you're paying a lot more for it. Okay? It's like saying you can get a seat in the theater in the back location here for $100. It's a lot of money, but that's the cheapest price. It's a very impressive show. But if you double it, if you go 200, you can go and sit in the middle. You double it again, 400, you can sit over here. If you double it again, 800, you're going to sit in that middle. See what's going on? So now if you pay $1,600, you're going to go this much. So now for $800, you're getting this much benefit. Before, for $100 extra, you got this much benefit. So law of diminishing returns. You're putting in the same amount, but your gain is less. So in this case, you're putting in, you're paying a lot of extra memory, but your collisions are falling just a small amount, insignificant, to make a big difference. Okay, so we looked at some typical ideas of how to do these hashing functions. I have some additional methods here. So let's say we have an original key is 1253. Let's take this number, let's square the number. If we square the number, we're going to get this big number here, 1,570,009. Let's take, for example, the 3 digits left of the second significant digit, so 1, 2, 3. So again, where this number comes, crazy number. Then we can extract these digits, so it gives us sort of a random behavior. Maybe we take this, maybe we cube this number. Whatever, we can do some crazy things to come up with keys. We also can do something known as radix transformation. Radix transformation simply means you're changing the base. Base 10 means 0 through 9. Base 2 means 0 through 1. Base 8 means 0 through 7. Hexadecimal means 0 through 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, F. We borrow from the alphabet to make our 10 through 15. So let's say the original key is 1253. So we can convert this to base 8. If we convert 1253 to base 8, we get 2, 3, 4, 5 octal. And then we can get the octal mod 101, which may be a prime number. We get this. So 101 is a prime. So this is just a conversion. So maybe we can square it and then make an octal. All kinds of things we can do. You try to just shake up, as much as possible to try to get some random behavior. Okay, let's do some hashing analysis. So this is going to be some simple probability. I think it's going to be kind of interesting for us to observe. We're going to make some very interesting observations in terms of what our expectations are with hashing. So let's make an assumption that we have n slots in the hash table. So n locations to put stuff in. Not chain, just regular, straight hash table with storage. We assumed that we have already hashed all the keys into the table. Okay? So given a particular hash table slot, so now we're going to look at our results. Given a particular hash table slot, so we have n of them. So we're going to choose this one right here. Why? Because it's as good as any other one. We're going to look at this one. It's the average one. And we're going to look at this, and basically there are two probabilities for any one slot. PRY is the probability that the hash table slot is chosen. And PRN is the probability that the hash table slot is not chosen. Okay? Now, if our probability function, if our hash table function really has a uniform distribution, that means the probability of any one slot being chosen is 1 over n. Does that make sense? Because that's the only way we're going to have equal probability across all slots. Which means the probability that the slot is not chosen is going to be 1 minus 1 over n, also known as n minus 1 over n. So if we have 100 slots, the probability of choosing a slot by a given key excuse me, is 1 out of 100. Whereas the probability of not choosing it is 99 out of 100. Now, if we look at the probability that 2 keys hash to a given slot, the probability that two keys. So I'm looking at slot I. What's the probability that these two keys are going to go into I? Well, the probability is that, right? Probability of yes followed by the probability of yes. Since those two probabilities are independent probabilities, the probability of both of them hashing to the same slot are independent and can be multiplied by each other. Because if everything is equally likely, the probability of the first key going to slot I is the same as the probability of the second key. Third, fourth, fifth, they're all the same. So therefore, my probability is going to be 1 over n times 1 over n, 1 over n squared. So, using a simple example with n equal to 100, my probability is 1 out of 10,000. So given two keys, the probability that they go to this slot is 1 in 10,000. How about this slot? 1 in 10,000. How about this 1 in 10,000? Because slots are all equally likely to get targeted by the function. The probability that the first key hashes to the slot and the second key to any other slot, if the first key hashes to the slot, that's the probability of yes. But the second one not hashing is probability of no. Well, that's going to be 1 over n times n minus 1 over n. That means the first one goes to the slot, the second one goes to any other slot. So that gives me n minus 1 over n squared. If n is 100, that's going to be 0.0099. Notice that the probability of yes is 0.01. So the difference between 0.01 and 0.099 is only 0.001. That's only 1/1000th, which is 1/10 of 1%. There's only 1/10% difference between the probability of the first one hashing to the slot, period, and the probability of the first one hashing to that slot and the second one not. It's almost the same probability. Why? Because the probability that not hashing to this slot is 99 out of 100, which is almost certain. As n is increasing, it approaches 100%. If n was 1,000, this would be 999 over 1,000, which would be 99.9%. Almost certain that the second one wouldn't. What's the probability that the first one would? 1 out of 1,000. Now, the probability that two keys hash to a given slot and two others do not, well, it could happen this way. You could have a yes, that means the first one goes to the slot, the second one goes to the slot, the third one doesn't, and the fourth one doesn't, which gives us the probabilities of 1 over n, y squared, followed by n minus 1 over n, that also squared. And then if n is equal to 100, that probability, I don't know what this is. This should be PRY squared, PRN squared, sorry about that, is equal to 0.00009801. But now we have to start thinking statistically. Because if I'm going to really ask the question, what's the probability of two keys hashing to a certain slot and two others not, having the yes, yes, no, no is a possible way of that happening. But there are actually many other ways that can happen. Because basically, because even if we have yes, yes, no, no, what if we had yes, no, no, and yes? Then the first one hashes, the second and third don't, but the fourth one does. Effectively, I still end up with 2. So if I really want to find out the probability that any two keys hash and any other of the two keys don't hash, then what I have to do is I have to find out all of the orders of yes, yes, no, no, which have 2 yeses. And those are listed here in the highlight. So this is the first one. This is where the 2 first go into the slot and 2 don't. Then you have a yes, no, yes, no, yes, no, no, yes, no, yes, yes, no, no, yes, no, yes, and no, no, yes, yes. All of these, there are 6 of them, all of these end up with 2 keys in the slot and 2 not in the slot. And I think you would agree that the probability of this and the probability of this is the same. In fact, the probability of this and this and this and this and this and this are all the same. Because all of them are going to have the same product. All of them are going to have 1 over n. All of them have the first 1 over n. All of them will have a second 1 over n. And all of them will have n minus 1 over n twice as a product. So they have the same value. So since each one has the same probability, the total probability is going to be 6 times the probability of one way of it happening. So our probability is rising to 0.000588806, which is still not super likely. What part of a percent is that? Not much, right? Because where's 1%? 1% is right here. There's a tenth of 1%. So this is 5/100 of 1%. Almost 600. So in general, let's see how we can generalize this for our analysis purposes. If we have R keys hashing, so not 4, not 5, not 6, R, we generalize it. R keys we're going to hash with the hashing function. And we want the probability that X of them are going to go to the given address, and the others, which is going to be R minus X, are not. So that basically gives us, one way of that happening is that the first X go to the hashing location, which means the probability of Y is multiplied by itself X times. X of them go, and then R minus X do not. But that is the sequence, yes, 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 followed by all the no's, which basically, going back to this, is basically this. But in actuality, having this occur can happen in a lot of different ways. And the number of ways it can happen is a binomial coefficient, which is, sometimes we call it the binomial coefficient, sometimes we call it the combinatorial coefficient. And basically, it's the combinatorial or binomial coefficient R into X. So another way of writing that is, you'll see, is using the binomial coefficient. We would have the R on top, X on the bottom. And we would read it, R choose X. This is called combinatorial coefficient of R into X. And this combinatorial coefficient is simply the first number factorial divided by the product of, this should be all division here, R minus X factorial times X factorial. So, given a set of R keys, the probability that a given address will be chosen X times will be the binomial coefficient of R into X times the probability of Y to the X power times the probability of no to the R minus X power. So this is the way we're going to end up. X matches, R minus X not matches, and this is the number of ways it can happen. Accounts for the full probability. And for our specific example, we would write it's going to be CRX times 1 over n to the x times n minus 1 over n to the r minus x. Does anybody have any questions about what this means and how this works? I can absolutely explain it if you need any more clarity. Make sense? Yep. Okay. So, the probability that a single key hashes to a given slot, we said was 1 over n. But since we're considering hashing not just one, but a sequence of r of them, so we're going to hash instead of 1, and have the probability 1 over n, we're going to hash r keys. So therefore, probability that a set of R keys hashes to a given slot is going to be R over n. Does that make sense? It's R times 1 over n. They're all independent. So think about n equal to 100. 1 over 100 is the probability. And I'm going to have 9 keys hashing. R is equal to 9. So probably the first one is 1 over 100, the second one is 1 over 100, next one is 1 over 100. So when I do all 9 of them, it's going to be 9 over 100. That's the likelihood of hashing to that slot. Notice that if R represents all the keys that I'm going to hash into the hash table, then R over N is also the packing density. Because if R is 100 and N is 100, then what's my packing density? What is it? 100%. If R is 80 and N is 100, then packing density 80%. If N is 800 and R is 600, then my packing density is what? 75%. 600 out of 800. So the packing density will be just R over N. R over N. So what we're going to do is we're going to use R over N as a replacement, and we come up with the Poisson probability, which is a closed form for P of X, which is P of X is equal to R over N, which is the packing density, to the power of X times e to the minus Rn over X factorial. This is the finished form of this, where N is the number of available addresses in the hash table, R is the number of records that we're hashing into the hash table, and X is the number of records assigned to a given address. Now, this can be developed by following the Poisson binomial distribution, where we're going to make the following substitutions. So the success rate we're going to call lambda is going to be N times the probability. N times the probability. So probability of the hashing. So P, solving for P, we get P is equal to lambda over N. Pardon, this kind of got messed up on my software, so pretty messed up here. Okay, so what we have here is we are having probability X is equal to K will be equal to N choose K. This will be the binomial coefficient. This is the combinations N into K, which is N factorial over K factorial times N minus K factorial. That's what this is all about. Times the probability, which is our hashing likelihood, to the K power, because we're looking for matching of K, times failure of the probability to the remaining elements, N minus K. Yeah, this is kind of messy looking. Man. I have another version of this. Let's see if I want to look at it or not. Let's see if I can get, I'd like to just get to, this is like a proof, so I don't really care. I think there are 2 versions of this up on Canvas, so if this is messed up, you know, so this is a little bit messed up. So the bottom line is, this is a little bit messy. The bottom line is, this is just a proof that this Poisson distribution, this one right here, this is a continuous distribution of a discrete function by taking the limit of n, which is the number of slots, to infinity. And once we do that, then we end up with this formula. So the formula essentially means that P of X is the probability that X keys hashed to a given location is going to be R over N, which is my packing density, to the power of X, which is the power of the elements, X elements going into that slot, times E times the negative power of the packing density R over N over X factorial. So I'm going to use this, so the next pages are just proofs of that's valid, and I'll give you a cleaner proof so you can look at it, but I'm not going to use what's up there now, it's messy. So let's look at an example. Suppose my packing density is 100%. If my packing density is 100%, what does it tell me about anything here? So no, R is not 100, N is 100. That means R over N is 1.0. So that means R is equal to N. That's what it means. So if packing density is 100%, that means R and N are the same, which means R over N is 1. That means this is really 1, right? Okay, so therefore it's going to be 1 to the power of x times e to the power of -1 divided by x factorial. What's x factorial? X factorial, whatever we want it to be. So how would we calculate the probability? Now, the important thing to understand is that, remember that our probability in the hashing analysis was 1 over n, and that was important because it guaranteed what important requirement for our best hashing function? Why is 1 over n such an important probability for us? With n slots, why is 1 over n such an important probability? Because it guarantees the equally likelihood of hashing to any one slot. So that is a probability. When you have R of them, it goes to R over n. This is also the packing density. This drives us to this Poisson function, where this is really the probability of x elements hashing to a slot. This is the probability that x keys hash to a slot. It's nothing more than the packing density to the x times e to the minus packing density over x factorial. Let's see if we can figure out what is the probability that one key hashes to a slot. Okay? The probability that one key hashes to a slot, but we'll assume that our packing density is 100%. If that's the case, then R over n is 1. So therefore, this will be equal to nothing more than 1 to the power of 1 times e to the minus 1 divided by x factorial, which is 1 factorial. Okay, so we can figure this out. So really, the whole problem is what? 1 over e, because it's going to be e to the minus 1. Everything else goes to 1. So, let me get a calculator here. So all I have to do is I have to do minus 1 and e to the power. And that gives me a number, which is a very important number for us. We're going to use this number again, 0.3678. 0.3678. Roughly speaking, 37%. I want you to interpret that number for me. So given R is equal to N, meaning the packing density is 100%, the probability of X is equal to 1 is equal to 0.368. Let's call it 37%. So I want you to interpret 37%. What does that mean?